So before going into the details of electrogravimetry, we need to first understand the concept, the actual meaning of the term electrogravimetric analysis. Actually, the term gravimetry, it indicates the weight of the material before and after the chemical reaction. So in general, we can say electrogravimetric analysis, it implies the weight of the material that is deposited after the process of electrolysis. So, in general or commonly, this is referred to as electrogravimetric analysis. Here, before there are going into the details, we should understand some important terms that are used in for we all know what is a cell. A cell consists of two electrodes that are dipped in an electrolyte, and basically there are two types of cell, that is a galvanic cell and an electrolytic cell. A galvanic cell is also called as a Daniel cell. In a galvanic cell or a voltaic cell, chemical energy is converted into electrical energy. The Daniel cell is an example of a galvanic cell. Now, in an electrolytic cell, when the energy is supplied from an external source, so whether the irrespective whether the cell is galvanic in nature or electrolytic in nature, the electrode where the oxidation occurs is called as the anode, and where the reduction occurs is called as the cathode. So this process and this terminology is irrespective of the type of the cells that has been used. So in general, we can say the electrode where oxidation occurs is the anode, and where reduction occurs is the cathode. So, suppose here an example is given when we consider a cell where copper is deposited at the cathode and oxygen is evolved at the anode. As you can see from the total overall reaction, here it is given that Cu gets converted to Cu2 plus. This double bridge vertical lines, it indicates a salt bridge. So at the cathode, the reaction that occurs is Cu2 plus, it gives plus two electrons to form Cu0, whereas in anode the HgO, it undergoes oxidation to 2H plus half O2 forming CO. So overall, this is the overall cell reaction that occurs in the cell. So the now we know how to calculate the potential of a electrochemical cell. That is given as E cell is equal to E cathode minus E anode, where the E cathode and the E anode, they represent the half cell potentials of the cathode and anode respectively. So first we need to calculate the half cell potential of both the respective electrodes, and then we can find out the overall EMF of the cell that is represented as E cell. Now suppose, as this is in figure 5.1, the general representation of an electrolytic cell is given. So here a voltage is applied to the cell such that the current flows through it. Now, generally speaking, the E applied of this that is applied to the cell, it must be greater than the EMF of the cell. Only then there will be a flow of current in the circuit. Now, when there is a current, the potential of the cell is less than the thermodynamic potential because of one of a very common phenomena that occurs, and that is like IR drop, concentration polarization, and kinetic polarization. So these are the three factors. These are the three conditions that invariably occur when there is current inside the cell, and this leads to a reduction in thermodynamic potential. So first we will know what is ohmic potential or what is IR drop. Now, most electrochemical cells, when a charge flows through it, they resist it. So, in both the type of conduction, the Ohm's law is given as IR. The product of the resistance of the cell in ohms and the current is called as the ohmic potential, or it is represented as the IR of the cell. So, we can just only write the resistance of the cell in ohms, the unit taken in ohms, and the current in amperes, it gives the ohmic potential, or we call it as the IR drop. So now when we know that if the applied potential is equal to the EM of the cell, then there is no current flow inside the cell. However, when we keep on increasing the applied potential, then the current flows through the circuit. Now this current, when it flows through the circuit, it encounters a resistance in the potential drop, that is minus R. So this implies that the applied potential must be greater than this ohmic drop, that is minus IR. It should be greater than IR, only then the current can flow inside the circuit. So mathematically we can say the E applied is equal to E cell minus IR. So and E cell can be represented as E cathode minus E anode. So therefore, overall we can say that E applied is equal to E cathode minus E anode minus IR, that is the IR drop. So, and this equation, if we further arrange this equation in terms of Nernst equation, then we can find that I is equal to minus E applied by R plus 1 by R E cathode by anode, and overall we can write it as I is equal to E cell minus E applied by R. So then further simplifying this reaction, the cell behavior can be written as I is equal to minus E applied by R plus K, where K is a small constant. Now if we look into figure 5.2, it is a plot of current versus potential. This is what we call it as the IE curve. So it is a plot. So what happens here is, as a plot of current, here it is plotted as a function of applied potential, and it should be a straight line. That's where the slope should be equal to the negative reciprocal of the resistance, that is the slope should be equal to minus 1 by R. Now as the applied voltage, as we can see from this figure 5.2, as we increase the applied voltage, the current deviates significantly, it deviates from linearity. Similarly, here as you can see in figure 5.3a, it shows the IE curve for an electrolytic cell. The current here, it deviates from linearity, and for an galvanic cell, it also behaves in the similar way. However, the deviation is differs in positive deviation and negative deviation for both the electrolytic cell and galvanic cell. Now, the cells that exhibit non-linear relationship, they are said to be polarized, and the degree of polarization is given by over voltage. So this over voltage is a very crucial term here in electrogravimetry, and we will in the next section we will discuss why this over voltage is important. So hence for an electrolytic overall cell, we can write E applied is equal to E cell minus IR minus over voltage. So simply putting this, over voltage can be defined as the potential difference between the theoretical cell potential, which is determined normally, and the actual cell potential at a given level of current. So over voltage just represents the difference that we have obtained from the theoretical calculation of EMF and the E applied that we have calculated by deducting the drop value, the IR drop. So and the difference in those values, it gives us the total value of the over voltage, which is an important factor. Now we need to understand what is polarization. So polarization is, if we suppose look into the graph given in figure 5.38, this is for an electrolytic cell. However, if we look here, as we increase the voltage along the x-axis, the current, it becomes independent of E applied. So this gives rise to a limiting current. This further the situation becomes so that the current becomes limited, and what we call it as the situation of limiting current. At this situation, the electrode is said to be completely polarized, since its potential can be changed without affecting the current. So polarization in this context has been divided into two categories. One is called as the concentration polarization, and the other is called as the chemical polarization or the kinetic polarization. So polarization is an electron phenomena, and it affects both either of the electrodes or both of the electrodes in cell, and it occurs very often in an electrolytic cell. So polarization is also an important concept in electrogravimetry. So now talking about the discussing further into polarization from figure 5.4, it is seen here we have a current versus IE plot, and the position of limiting current is indicated by this. This is a very important point in deducing the electrogravimetry. So concept here we have, as we talked, there are two types of polarization. One is concentration polarization and other is kinetic polarization. So coming to concentration polarization, this implies that suppose in an electrolytic cell, when the ions are discharged, they are and deposited on the electrode. So what happens is that the area in the nearby areas of the electrode that becomes devoid of ions, and the layer offers a resistance to the current flow to it. So this type of resistance that is offered by the electrode due to changes in concentration of the electrolyte is known as concentration polarization, and this occurs when ions do not arrive at the cathode or the products do not leave the anode fast enough so as to maintain the desired current. So this is the case of concentration polarization. Now we have already know that reactants are transported to an electrode by three mechanisms. One is diffusion, migration, and convection. So concentration polarization, it arises when the effects, these three effects, that is the diffusion, migration, and convection, they are insufficient to transport the electrons at a rate that produce the current of desired magnitude. So if the depleted area of the electrode is not supplied with the incoming ions, then what happens is the bulk solution of the bulk of the solution is increased by stirring. So in most of the cases of electrogravimetry, the stirring or agitation is mainly preferred. As a result of this stirring, the cathode, it assumes more and more negative potential as the applied potential is increases. So because of this, a back EMF is set up, and the concentration polarization tries to overcome the effect of concentration polarization, and an equilibrium is tried to achieve. So concentration polarization, it requires applied potentials that are both theoretical to maintain a given current in a electrolytic cell, and this is why, for this reason, to avoid the concentration polarization, various stirring and heating are important factors in the electrodeposition process. So the two main factors that need to be considered for a electrodeposition process is vigorous stirring and heating. Mostly in all the cases, stirring or mechanical agitation is very rigorously followed. So the next case is kinetic polarization, or what we call it as the chemical polarization. This occurs due to the changes in the chemical nature of the electrodeposition of another metal, or due to the coating of the electrode with a layer of gas, maybe hydrogen or oxygen. Kinetic polarization is also caused due to the formation of films on the surface of the electrode. Like for example, an aluminum anode, it is susceptible to be passivated by a coat of alumina on it, because since aluminium is highly sensitive to the oxygen present in its surrounding, so in most cases it is likely to be covered by a coat of aluminium oxide, that is alumina on it. So this also leads to kinetic polarization or chemical polarization. Kinetic polarization is most pronounced in electrode that possess gaseous products. This is very common when gaseous products are involved. So this is known as gas over potential. Gas over potential depends on several factors such as electrode material, the current density, the temperature, the pH of the solution, and other factors. The over potential also is different for different types of metal, since it is highly dependent on the nature of the metal that is employed. The over voltage at a given current density decreases if the electrode surface is roughened. So an increase in current density, overall it increases the over potential. As the temperature increases, the voltage also decreases. So hydrogen over voltage is greatest in metals such as cadmium, lead, tin, zinc, mercury, and pH of the solution is also one of the factors that has an impact on overpotential. So one of the essential requirements of electrodeposition is that the deposit must be very compact, fine, and adherent to the electrode. In addition to this, the deposit must be pure in nature and free from any impurity, any traces of impurity. So simultaneous evaluation of gas in the cell, it also results in a very spongy type of deposits. So even if you employ higher current density, then the applied potential, it exceeds the hydrogen over voltage and it leads to gasification. So gasification can be avoided by controlling the actual potential and the other parameters. So the complex ions yield smoother deposits. Like for examples, when silver, when deposited from silver cyanide, it yields a very satisfactory deposit. So these are some of the factors that need to be considered during the process of electrodepositing. Now we need to know the importance of overvoltage. The existence of overvoltage, it explains various types of phenomena. Like in a lead accumulator, during the charges process, the metal is deposited on the cathode instead of hydrogen being evolved due to high overvoltage of lead. It is possible to deposit electrolytically the metals which are have more negative potential than hydrogen, such as zinc, cadmium, because of high overvoltage of hydrogen on such metals. Overvoltage also plays an important role in the industrial production of chlorine and sodium hydroxide by the electrolysis of brine sodium chloride solution. When electrodes of high over voltage, they are used in electrolytic reduction, it means to increase the reducing power. This means that electrodes with high over voltage like lead, they can be used instead of platinum for organic electrolytic reductions. And this, the over voltage has been a great factor for economical factor, because it can be, because the use of platinum can be totally ignored and lead can be used for organic reductions, since platinum is expensive and lead is a very cheaper metal on the other hand. So this over voltage also is no, it is not only beneficial but also it is economic in nature for various types of organic electrolytic reductions. Now, coming to the types of electrogravimetric methods, electrolytic precipitation, or that is commonly known as electrodeposition, they have been widely used for determination various types of metals. Like in most applications, the metal is deposited on a weighed platinum cathode, and the mass and the increase in mass is mostly determined, since gravimetry employs the mass, the weight of the material. Here we calculate the metal that is deposited on the cathode after the process of electrolysis. Now, in general, there are two types of electrogravimetric methods, one which occurs at constant current and the other which occurs at constant potential. So, talking first, we will talk about constant current electrolysis. In this method, the experimental setup is shown in figure 5.5. So here the apparatus for constant current electrolysis, it comprises of a cell and a DC source. The DC source is the power source, and emitter and voltmeter are also connected. The voltage applied to the cell is controlled by a resistor, and the cathode is usually a cylindrical platinum gauge. In most of the cases, platinum gauge is taken as the cathode. Now, the physical characteristics of the metal deposits by this process. So it is always important that the deposits by electrolysis, they are pure in nature and strong and smooth, so that they can be used without any mechanical loss. So very spongy or powdery type materials or deposits, they are likely to be less pure, and they are also not very warranted in our day-to-day lives. So that is why the primary aim of electrodeposition is that the material should be pure and strong in nature. So as mentioned earlier, the principal factors that influence the physical characteristics of the deposits, they are mostly current density, the temperature, and the presence of complexing agents. Now, the best deposits, it has been found that the best deposits are formed when current densities are less than 0.1 ampere per centimeter square. Now, we know, just as we had discussed before, stirring or heating generally improves the quality of the deposit. Further, the time of deposition is reduced when the solution is stirred vigorously or if the electrode is rotated at a uniform speed. This type of stirring, it lowers the concentration over potential and enables a higher current density without any adverse effect. Now, as a result of this stirring, the an uniform deposit occurs, and the uniform deposit is maintained throughout the electrode. And further, the higher current density is also, it lowers the concentration over potential. So simultaneous evaluation of gas at an electrode during deposition is not desirable. That is why, if sometimes we have the porous and spongy deposits are also obtained if we have evolution of gas during the process of electrode deposition, and thus it should be avoided at any cost. So the chemical nature of the ion in solution, it also has an important influence on the deposit that is obtained. So for example, like a pure and bright copper deposit is obtained by electrolyzing a solution of cupric ions in nitric acid. However, in contrast, a coarse tree-like deposit of silver is obtained if we electrolyze a solution of silver ions in nitric acid. So now we see that the chemical nature or the nature of the electrolyte that is used is different for different electro deposition processes, and it also depends on the metal that is employed. So complex ions, they exhibit a property that is known as throwing power. The property of this solution is by virtue of which a deposit, when it is obtained with very irregular and dented surfaces, they often provide the best deposits. So this is known as the throwing power. When we talk about increase in temperature, we know that a temperature rise, it favors the diffusion process, but the hydrogen over potential is decreased and the stability of many complex ions is decreases. So in practice, constant current electrolysis is limited to the separation of an easily reduced cation from cations. Thus, Cu2 plus can be deposited from an acid solution, and mostly it is employed for constant current electrolysis. Now, the potential changes during electrolysis that we talked about, the electrolysis process that occurs at constant potential. Right, this is the second case. As we look into figure 6.b, let us consider the electrolysis of copper. So, initially, the applied potential which leads to current has been shown in figure 5.6a. So here, as in this process, the figure 5.6a, it represents the current time plot. The electrolytic deposition of copper is then completed at this applied potential. So as we see, as the reaction proceeds, the IR decreases continually. So this decrease is due to the concentration polarization which we had discussed earlier. The decrease in IR, thus it must be compensated by the increase in cathode potential, since the cell potential here it is constant. The increase in cathode potential is slowed down at point B due to the reduction of hydrogen ions. So as here the solution, it contains a large excess of acid, that is no longer it is susceptible to polarization. Under these conditions, the cathode is said to be depolarized by hydrogen ion. So this, in this process, the here the electrolysis which occurs at constant potential, at the cathode turns to be depolarized by the hydrogen ions that is present in the solution. So when we consider a case of Cu2 plus and Pb2 plus, now as shown in this figure B. So lead in figure 5.62b. Now the lead, it begins to deposit at point A as shown here. This is point A. So hence lead ion would begins to deposit at the cathode potential curve. The lead ion would co-deposit before copper deposition was complete, and thus there would be an interference. The co-deposition of hydrogen during the electrolysis, it leads to formation of very bad deposits. The deposits that are formed here, they are not very strong in nature. Such a situation is unsatisfactory. Thus in this case here, since there is an interface, interference, the use of depolarizers is used as they improve the efficiency of the process. Now a depolarizer is a substance which gets reduced at the cathode without gasification, and or it can be oxidized at the anode, and thus they stabilizes the potential or and minimizes the concentration polarization. Thus copper deposited from nitric acid solution is smoother and more adherent because nitrate ion acts as cathodic depolarizer. So generally reducing agents like hydrogen hydrochloride, they act as anodic depolarizer. So the cathodic depolarizer, nitrate ion, gets reduced at a potential less than this and is generally represented by this equation. The nitrates ion, they have most very long, they have been used in constant current deposition of copper and lead, where copper is deposited at the cathode and lead is obtained at the anode as lead dioxide. The nitrate ions, they aid in the quantitative deposition, and here in table 5.1 it shows the typical applications of constant current electrolysis. Now, from table 5.1, you see for when the analyte is Ag plus and the platinum cathode and anode is taken, and the conditions are maintained as alkaline cyanide solution, the product, the deposit that is made is silver. Now, similarly, when copper 2 plus is taken as analyte, in the cathode and anode are taken as the platinum electrodes, and the cell react and the cell conditions include H2SO4 and HNO3 solution, the deposit that is made is copper. These are examples of various applications of constant current electrolysis that are commonly being used. Now, here we'll talk about constant potential electrolysis. So here some of the after these are the examples shown in figure 1 are some of the typical cases that uses constant current electrolysis. Now constant potential electrolysis implies that here the potential needs to be controlled. So by this electrolysis it is possible to separate two elements whose deposition potentials differ very sufficiently. They have a large difference in their deposition potential. So the potential of the cathode is controlled, so it never becomes sufficiently negative to allow the deposition of the next element. So as you can see, when we look into figure 5.6b, at the cathode, at the potential of the cathode becomes negative due to the concentration polarization, and since co-deposition occurs, the large negative drift in the cathode is avoided by using a three electrode system as shown in figure 7. So this is what is called the controlled potential electrolysis, and the three jacket electrode system is shown here. The here in controlled potential electrolysis, it consists of two independent electrode circuits and that have a common electrode, where the working electrode, it has a common electrode and a working electrode at which the analyte is deposited. A DC source is provided, a potential divider is also provided that provides the that permits or allows the variation in potential applied across the circuit. A counter electrode and a current meter is also present here. The reference circuit or a reference electrode, that is standard calomel electrode, a high resistance digital voltmeter and a working electrode is taken. The electrical resistance of this circuit is so large that the electrolysis circuit, it supplies all the current that is required for the deposition of the metal. The current in the reference electrode circuit is totally zero at all times. So in this case, the purpose of the reference circuit, it is to monitor the potential between the working electrode and the reference electrode. Now when this potential reaches at a point at which the code deposition or the interference is about to begin, this potential, it moves from one point to the other, and since the potential remains constant during this change, the cathode potential becomes smaller. Thus, it prevents the co-deposition and therefore leading to non-interference between the two metals. So, as shown in figure 5.8, this is the change in cell potential and current during a controlled cathode potential deposition of copper. So, here the changes in the cell potential and control has been shown. The applied cell potential, it has to decrease continuously throughout the electrolysis, which diminishes, makes the current almost equal to zero. So after the completion of the electrolysis, the current will be approaching to zero. This indicates that the electrolysis is complete. This technique demands constant attention during operation. Usually some there has been some automatic control. However, this method is time consuming and demands constant regulation during the process of being carried out. So the electrodes that are being used here, usually platinum gauge electrodes have been employed because they have advantages of being inert and they are relatively non-reactive. They cannot be ignited, and they cannot be they have this ability to be to remain. They are not susceptible to acidic or alkali attack, and the gases that might have deposited on the surface of the platinum electrodes can be removed just by igniting. Certain metals like bismuth and zinc, they cannot be deposited directly on platinum. Okay, since they cause permanent damage to the electrode, that is why a thin coating of copper is always deposited on the platinum electrode to prevent its further degradation. So it serves as a protection barrier to the platinum gauge electrodes. Hence, a thin protective coating of copper is always deposited on the platinum electrode that is employed for this electrogravimetry process. Now, mercury cathode is also used, and it is particularly used for removing reducing metals in preliminary steps. For example, copper, nickel, cobalt, they are readily separated from at these electrodes by using ions such as Al3 plus, Ti2 plus, the alkali metals, the sulfates and the phosphates. The precipitated elements, they dissolve in mercury with little hydrogen evolution, because mercury has a high hydrogen over voltage, and hence no hydrogen evolution occurs even at high applied potentials. So the advantages of using a mercury cathode is that it forms an amalgam with the various number of metals that are used. And since the hydrogen high over voltage is, it has a high hydrogen over voltage, so the chances of the evolution of hydrogen gas is totally neglected, even at very high potentials. Now, the application of controlled cathode potential, it is very useful in the separation of quantitative determination of metallic species. Among the this particularly the controlled cathode controlled cathode potential electrogravimetry has been used for deposition of metals and separation of successive metals. So it involves mostly the these steps. Successive, first, a mixture. For example, if a mixture of copper, bismuth, lead, they can be determined by successive deposition of the metals on a platinum cathode. First, we deposit the cathode copper at the cathode by normal, using the cathode potential at minus zero point 0.2 volt versus the standard calomel electrode. After weighing the cathode, the copper plated cathode is used to deposit bismuth at a potential of minus 4 volt. Then lead is deposited over the same cathode by maintaining a cathodic potential of minus 6.4 volt. Now a minus 0.6 volt. So all these elements, they are deposited from neutral solution containing tartarate ions, which form the complex with tin and prevents the deposition. After, when the lead deposition is complete, the solution is made strongly ammoniacal, and cadmium and zinc are deposited successively at minus 1.2 volt and minus 1.5 volt respectively. So you here we can see one by one metal, they are deposited successively at the cathode. So there are also possibility of using simultaneous depositions, a mixture of copper and lead that can be determined by the deposition of copper in the presence of nitrate ions. So lead is deposited as lead dioxide at the anode. So in both the cases, we can see, once we can follow the successive deposition of metals, and in other cases we also have simultaneous deposition of metals. So both types are possible. Then it is also used in preparatory organic chemistry. So if an organic compound that is subjected to a series of reactions, redox reactions, whether reductions or oxidations, particularly at a definite potential, then it is possible to reduce the starting material to the desired product by controlling the whole potential of the solution during the process of reduction at the cathode. This type of electrolytic reduction is much more economical than chemical reductions, where side reactions also produce undesired products. As you can see, in the use of electrolytic reduction is beneficial, as it totally eliminates the use of the undesired products that are formed in conventional chemical reactions. So table 5.2, it shows the applications of controlled cathode potential electrolysis in various cases. So, like from if the analyte is Cu2 plus and a platinum cathode is taken and the condition is used as H2SO4NO4, sorry, H2SO4HNO3, then we get copper. So these are some of the examples of controlled cathode potential electrolysis. So next we will talk about is coulometry. Coulometric methods of analysis, these are based on the measurement of quantity of electrical charge that passes through a solution during an electrochemical reaction. This principle is basically governed by the Faraday's laws of electrolysis. Now first we should need to know what are the Faraday's laws of electrolysis. So the two laws have been postulated by Faraday's, and the Faraday's first law of electrolysis, it states that the mass of a substance which is liberated at the electrodes during electrolysis is directly proportional to the quantity of electrical charge Q that is passed through the electrolyte. That is, mathematically, if m is the mass of the substance that is deposited by the current u of I amperes and t in seconds, then applying first law of electrolysis, m is directly proportional to q or m is directly proportional to I into t. So which implies m is equal to z I t. Z implies a proportionality constant. So thus the first law states that the quantity of current passed and the extent of chemical change that took place. The second law states that the mass of different substance evolved or deposited by the passage of same quantity of current electricity are proportional to their chemical equivalence. That is, m is directly proportional to m by n. That is the equivalent weight of the substance, where m is the mass of the substance that is liberated or deposited, and mr is the molar of the substance, and n is the valency, which we can directly write it as m is directly proportional to the equivalent weight of the substance. If m1 and m2 are two different substances liberated by same amount of electricity, and m1 capital m1 and m2 are their respective molar masses, and n1 and n2 are their respective valence numbers, then m1 by m1 is equal to m2 n2 by capital M2. So like for example, here an example is given. Let us consider the passage of electricity through solutions of copper sulfate and AgNO3 that are connected in series, so that the same amount of electricity is passed through it. So from the second law, we get that the mass of copper deposited divided by mass of copper is equal to mass of silver deposited by molar mass of silver. So here in the case of copper, 2 is multiplied owing to the valency of Cu and so forth. And here the mass of silver has been multiplied by 1. This is the valence number of ions. So the quantity of electric charge is equal to the product of current or charge and time for which it is passed. That is, we know that q is equal to I into t, and the practical unit of electricity is coulomb, represented as C. So when a current of 2 ampere it flows for 10 seconds, then the quantity of electricity q can be represented as I into t, that is 2 into 10, that is 20 coulombs. So it is always important that we note the unit of current and the unit of time to find out the value of q, that is the quantity of electricity. So now for a variable current, I is the electricity. So let us understand what is the term F, Faraday. F, the quantity of electricity that is carried by 1 mole of electrons is called as Faraday, and it is given by the symbol capital F. Now we know the charge of an electron is 1.6 into 10 to the power minus 19. Therefore, the charge on 1 mole of electrons will be 1.6 into 10 to the power minus 19 into Avogadro's number, that is 6.023 into 10 to the power 23, which gives the value 96485 coulombs. Hence, we have taken 1 Faraday to be approximately equal to 96500 coulombs. So 1 F is equal to 96500 C. Now let us consider a common equation that Mn plus, it takes n number of electrons to give the M. So the quantity of electricity that is required for deposition of 1 mole of an element will be equal to Nf, where N is the number of moles of electrons that is required for the reaction. Now let Mr be the relative mass of the atomic mass of 1 mole of the element. Hence, for deposition of Mr or 1 mole of the element, we require Nf of electricity. That is, small m is equal to the relative atomic mass into Q by 96500 into small n number of moles gram. So this, arranging the above equation to find out the mass of an element that is deposited by the passage of q coulomb, we write it as mr into I into t by 95600 n. This equation is very useful for the calculation of the deposition of a mass of an element by the passage of a known quantity of current. So if we know the amount of quantity of current, that is I, and the time it is passed through it, the q value, then we can find out the mass deposited by that much amount of current over the electrode. So this is the equation 5.13, is a very important equation depicting how to calculate the amount of mass electrode deposited. So next, coming to the use of a coulometer. So in coulometry, the coulometric methods, they are actually based on the measurements of quantity of electricity, that is Q. In other words, the quantity of electricity that is needed to complete the electrolysis, it is a measurement of the amount of analyte present in the solution. A coulometer is particularly a device that is used for measuring the quantity of electricity that is required to bring a chemical change in the analyte. So there are various types of coulometers are available, like gasometric coulometers, hydrogen oxygen coulometers, gravimetric coulometers, and other coulometers like silver coulometers, titrimetric coulometers, iodine coulometers, etc. Now we'll start with gasometric coulometers, or that is hydrogen oxygen coulometers. Hydrogen oxygen coulometers, they consist of two platinum sheets that are joined with, and the platinum wires, they serve as the electrode. So here in the, they are connected to atmospheric pressure, and zero point 0.5 molar solution of potassium sulfate is taken as the electrolyte here. On electrolysis, the following reactions occur at the anode and cathode. At anode, oxygen is liberated, and at cathode, hydrogen is liberated. So the overall reaction is given as the 3 moles of gases, that is 2 mole of hydrogen and 1 mole of oxygen, they are produced by consumption of 4 faradays, which is equivalent to 0.17 centimeter cube at ntp. So this, these two find out the actual volume to be 0.1739 centimeter cube. Such coulometers, they show an accuracy of about minus 0.1%, and the at low current they cause negative errors. It has been reported that the loss of efficiency is mostly due to the formation of hydrogen peroxide at the anode. Else, this is a very sophisticated instrument and it provides greater accuracy. So there needs to be certain precautions that need to be adopted for oxygen hydrogen coulometer. The first is the gas burette should be water jacketed and the temperature should be within plus minus zero point 0.1 degrees centigrade. The electrolyte must be pre-saturated with oxygen and hydrogen mixture, and during the course of the reaction, the gas burette must be lowered periodically to hold the gas pressure close to the atmospheric pressure so that the equilibrium is maintained inside the coulometer. So now next, coming to silver coulometer. It is an example of a gravimetric coulometer which measures the amount of metal deposited at the cathode or the amount of metal that is removed from the anode. So here a silver coulometer is shown in figure 5.11. This is one of the most satisfactory. It is either in cathodic deposition or in anodic stripping or in perchloric acid media. So here a rod of pure silver in a porous pot, it acts as the anode, and the current density is mostly maintained at 0.2 degrees centigrade. The increase in mass at the cathode gives the amount of the silver deposited. From the mass of the silver deposited, we can find out the coulomb involved in this reaction using the above equations. Now, in a iodine coulometer, it is an example of a titration coulometer where anodically generated iodine is titrated with thiosulfate or arsenic solution. This has been mostly used in the determination of Faraday constant. Then we have colorimetric coulometers. They are based on the principle of developing a colored species with a reagent with a metal that may be anodically stripped. For example, the formation of a colored species of cobalt with nitroso R salt and the measurement of absorbance with a spectrometer. So a metal ion may be cathodically reduced and subsequently the absorbance must be measured. So here reduction of iron 3 at the cathode and measurement of followed by its absorbance with a particular chemical reagent is done, and then the quantity of current is measured by this is called as colorimetric. As the name implies, colorimetry is always associated with a spectrophotometer. Then we have radioactivity coulometers. So it is a microcoulometer which is based on counting the deposits of one Ag110 that has been described. The unknown silver solution, it is first spiked with a known solution of the radioactive silver, that is Ag110, and then the deposit is made on a platinum wire which also contains radioactive silver. So equal amount of silver are plated on each cathode. The ratio of the radioactivities, it gives the amount of the silver in the unknown cell solution. The cell containing the radioactive silver is the radioactivity coulometer. This method is useful for small quantities and particularly used for radioactive elements. So the above types of coulometers can be briefly, they can be put in an electrolytic solution and can be used as a mostly used for measuring the quantity of current that flows through the cell. So now coming to different types of colorimetric methods. The coulometric methods can be classified into following two categories. One that occurs at constant current coulometry, or that we call it as amperostatic coulometry, and the other that is controlled potential coulometry, or that is potentiostatic coulometry. In amperostatic coulometry, it further occurs as primary coulometric analysis and secondary coulometric analysis. For potentiostatic coulometry, it is called as coulometric titration. Okay, and then for secondary coulometric analysis, we have external generation analysis and internal generation analysis. So two general techniques are used for coulometric analysis, that is amperostatic, and the other which occurs at controlled potential or constant potential, that is called as potentiostatic coulometry. So in constant current coulometry, the current is maintained constant till the completion of the reaction occurs, and it is indicated visually or by potentiometric or spectrophotometric methods. The quantity of electricity that is required to attain the endpoint is derived from the amount of the coulombs that is consumed and from by utilizing the previous equation. So primary constant current coulometry, here the element to be estimated, it undergoes direct reaction at the electrode with 100% efficiency. At the secondary constant current coulometry, it has a wider application, and here one of the reactants that is generally is generated at an electrode which then reacts with the analyte ion to be estimated. A titration, for example, a titration of ferrous ion versus ceric ion is an example of a coulometric titration. Let us consider the oxidation of iron 2 at the platinum electrode. So the primary anodic reaction is Fe2 plus giving rise to Fe3 plus E. In constant current electrolysis, towards the completion of the reaction, there is an increase in the applied cell potential. Because of the concentration polarization, the increase in cell potential, it causes the anode potential, which causes the decomposition of water to O2 plus 4H plus 4E. Hence, for the completion of the reaction, the oxidation of iron at platinum electrode is not achieved. So, the current efficiency of such a process is less than 100%. Now, here we, by introducing an excess amount of cerium 3, which is oxidized at a lower potential than that of water, a coulometric determination of iron can be achieved. That is Ce4 plus Fe2 plus, giving rise to Fe3 plus C3 plus. So the steric ion that is produced by the oxidation of serous ion at the anode, it diffuses out. This one, the C3 plus, it diffuses out and reacts quantitatively with the ferrous ion and oxidizes to ferric ion. The net effect is an electrochemical oxidation of iron with 100% current efficiency. Now, coulometric titrations have become more popular because of the in situ generation of these reagents. For example, halogens have been most found to be satisfactory for the coulometric titrations. Now, coming to potentiometric coulometry, which occurs at controlled potential coulometry. So here the potential of the working electrode is held constant so that quantitative oxidation or reduction occurs. The current is initially high but decreases rapidly and approaches zero to the end of the reaction. The quantity of electricity is most commonly measured with an electronic integrator or from the reading of the series in the cell. So certain special features of coulometric methods, they give more accurate and precise results. They are suited for routine as well as much more complex analysis. They are more popular and they have the special advantage of, because they do not have the tedious steps of preparation and handling is easier. Titrations which cannot be performed by conventional methods, they have been performed coulometrically. The in situ generation of titrants, they like have been found to give the most satisfactory results for various organic compounds. Constant current coulometry is also, it is actually more useful than the controlled potential coulometry because it is faster and inexpensive. Controlled potential coulometry is also quite sensitive tool and is more selective. Now, coming to potentiostatic coulometry, the principle states that the potential of the working electrode is held constant. It is not zero, but it is held constant. This technique is also similar to that of electrogravimetry, where the electrolysis occurs at a fixed potential. Controlled potential technique is therefore can be applied to systems where poor deposits are yield. So that is why it has been used for the detection in antimony deposits. Now, the instrumentation for potentiostatic coulometry is given in figure 1.2, that uses a platinum gauge and a mercury pool. The cell assembly, it consists of a platinum gauge working electrode, a platinum wire counter electrode, and a SCE, saturated caramel electrode, as the reference. The counter electrode is prepared from the test solution by a porous tube that contains the same supporting electrolyte. So the potentiostat, sometimes a mercury has been used as indicated in the figure 5.12b. For copper, nickel, cobalt can be easily separated from these processes by using the mercury electrode, and they, because they can be most easily precipitated in the form of their amalgams. So a potentiostat is an electronic device that maintains the working of a, that maintains the potential of a working electrode. So this in figure 5.13, it shows a schematic of a potentiostatic coulometry. So when we consider the two resistance in the diagram of the electrochemical cell, the path between the inverting input and the circuit common at the output, we find that E2 is equal to ESCE plus EC. So where EC is the cathode potential and that is equal to the potential difference between P of the working electrode. So overall, if we look into the mathematical representation, it is given as E2 is equal to ESC plus EC, SCE. The practical circuit, the in most of the modern apparatus for potentiostatic coulometry, they employ integrators to define the number of coulombs required to control an electrolysis. So efficient stirring is important for controlled potential electrolysis. Besides stirring, the ratio of the electrode surface to solution is also important. This ratio plays an important role, and is the and the is also, it is given by the mathematical formula C I is directly proportional to C into A. Now, since we know that Q is equal to I into T, so Q is equal to I into T, that is directly proportional to, since I is equal to C into A, we can write that Q is directly proportional to C into A into T. So the various applications of controlled potential coulometric analysis has been in inorganic chemistry. As many as 55 elements can be determined by these processes. It is also widely used in analysis of radioactive elements. This has been used in microanalysis studies, like of by use for the determination of very minute quantities of analytes. So that is usually referred to as microanalysis. The determination of several metal ions in the same solution is also possible by this, called the multi-step control potential electrolysis. It is a continuous monitoring gas streams. It helps in the determination of trace level of concentration of the various gases present in the solution. So now it is also used for electrolytic determination of organic compounds. Controlled potential electrocoulometry is also helpful in the electrolytic synthesis of new organic compounds. No chemical reagents are required, since electron itself is the reagent that is used for carrying the conventional chemical processes, and in electrolytic synthesis no contamination occurs. It is also useful for determination of n values of the reaction. The n values, they offer a route to deduce the kinetics and mechanisms of any reaction. So here, by the electrolysis process, by coulometry process, we can find out the controlled potential coulometry. It also helps in finding the value of n. So constant current coulometry, that is amperostatic coulometry. This technique is better known as coulometric titration. In a coulometric titration, a titrant is electrolytically generated and it reacts stoichiometrically with another and proceeds with almost 100% efficiency. It involves a single chemical change that it involves a single chemical change in the analyte. Coulometric titration has a special advantage in a sense that the standard solution is not required. This is also very useful for estimation of various quantities of substances in micro amount. So figure 5.15, it depicts the schematic of a coulometric titration. So a source that is at constant current, which we generally call it as amperostat, is provided, and the switch that initiates the current are required. The potential drop across the standard resistor is also used. Many electrochemical and commercially available amperostats are available in the market. So this is quite easily available. Now the cell assembly, it consists of a generator electrode as shown in figure 1.6, the 5.16. The products formed at the second electrode, it interfere with the electrochemical reaction. For example, the anodic generation of oxidizing agents like C3 plus to C4 plus is often accompanied by evolution of hydrogen. This hydrogen then reacts with the oxidizing agent and leads to a positive error. Hence, the electrode is isolated and by a sintered glass disc. Besides this, the arrangement also helps to maintain a 100% efficiency. Then external generation of titrant. Since the internal generation, it interferes with titration, it is becomes crucially important to generate the titrant externally and deliver it outside of the reaction cell. An assembly is shown in figure 1 5.17. Here hydrogen and hydroxyl ions, they are produced by the electrolysis. So here the cell consists of two electrodes of platinum gauge which are separated by a sintered glass. The here the apparatus is so arranged that the flow of electrolyte, it continues even after the current is discontinued, and then the residual reagent is flushed out into the titration vessel. This type of external generation apparatus has also been used in the generation of other reagents. Thus coulometric titration are beneficial than conventional volumetric titration in this regard. It should be noted that the generation of reagents is possible only if the titration is generated with 100% current efficiency. Then the most important part is detection of endpoints in coulometric titration. The detection of endpoints is quite satisfactory. For example, the detection can be done with starch, or that involves iodine titration. Detection with methyl orange can be done, that involves hydrazine hydroxylamine. However, coulometric endpoint can be more accurately determined by instrumental methods of detection such as potentiometric, conductometric, and here. The potentiometric endpoint detection has been found to be suitable in acidimetric and redox titration. The amperometric detection of endpoint is useful in redox and precipitation reactions. The spectrophotometric endpoint has been developed, and this is of great importance. The exact endpoint is usually determined by extrapolation of the linear portion before and after the endpoint. By proper choice of lambda max and molar absorptivity, the sensitivity and selectivity of the methods can further be improvised. Now, the applications of colorimetric titration, they have been developed for all volumetric titrations. The first is neutralization titration. Titrations of strong acids with weak acids with hydroxide ions they generated at a cathode have been developed following this reaction. The endpoints can be detected by the use of indicators. However, potentiometric endpoints can also be employed by using commercially available instruments. A real advantage of such colorimetric titration is that the interference for carbonates can be avoided. Plus, secondly, they are used in precipitation and complex formation titration. A large number of colorimetric titrations have also been developed with anodic generation of silver ions. The oxidation reductions, they are also used in oxidation reduction, that is redox titrations. The oxidizing reagents such as iodine, bromine, and such, they and the unusual oxidation states they can be generated by making use of the colorimetric methods. So the colorimetric titrations assume importance because of the possibility of the in situ generation of the reagents. Conventional volumetric analysis cannot handle or prepare these reagents. Now, as shown in figure table 5.3, these are certain applications of colorimetric titrations involving neutralization, precipitation, and table 5.4 shows the applications of colorimetric titrations involving redox reactions. So these are some of the advantages of colorimetric titrations. The preparation standardization, they are not necessary. The handling is easy. A single constant current can be used for generating for all the process. Colorimetric titrations can be readily adapted. A number of automatic colorimetric titrators are readily available in the market. In chloride titrator, silver one is generated colorimetrically. In carbon dioxide monitors, in which the gas stream absorbed in monoethanolamine is titrated with colorimetrically generated base. In water titrators, that is Carl Fisher reagent, it is generated electrolytically to determine the trace level of water content or moisture. So these are some of the important applications of colorimetry. So in summary, we can say the advantages of colorimetric titrations and applications has been well discussed here in this chapter. So now we will take a break of 5 minutes and further resume with the, the applications of electrogravimetry. So now coming to Unit 6, that deals with the applications of conductometry, electrogravimetry, and coulometry. In this unit, we will talk about the various applications that we have discussed above before. So we'll discuss in details the applications that we have come across. So first we will start with the degree of dissociation of a weak electrolyte and its dissociation constant. Now, when we talk for a weak acid, that is Ha, the equilibrium is represented as Ha that breaks to give H plus and A minus, where at equilibrium the concentrations for Ha is given as C into 1 minus alpha, and H plus and A minus are given as C alpha, where C is the concentration of the acid and alpha is the degree of the dissociation or the degree of ionization. So considering the thermodynamic equilibrium constant, that is Ka, it can be written as approximately concentration of H plus into concentration of A minus by concentration of Ha. Now, from equation 6.1, we see that concentration of Ha is equal to C into 1 minus alpha, and concentration of H plus and A minus is C alpha. So, when we substitute these values in equation 6.2, we find the value of Ka to be alpha square C by 1 minus alpha. And this is called as Ostwald's dilution law, which gives the dissociation constant considering the degree of dissociation. Now, similarly, this Ostwald's dilution law can also be given for the dissociation of a weak base, which finally gives that Kb is equal to alpha square C by 1 minus alpha. Kb represents the dissociation constant for a weak base. Now let us consider the discussion of the dissolution of dissociation of a partially soluble salt, that is Ma, where Ma dissociates to form M plus and A minus, and similarly the Ks, that is the solubility product for this salt, it can be written as H plus into A minus. So with this background, we all know this, the we will see how the dissociation of a weak electrolyte can be determined by using conductometric methods. Now, after the derivation of this Ostwald's equation, we also have the relations, that is lambda m is equal to alpha into lambda to the power alpha. So the lambda here, the molar conductivity of a very weak electrolyte, it is expressed by the product of its degree of dissociation and its limiting molar conductivity. That is lambda m can be given as alpha, which is the degree of dissociation, and lambda to the power alpha. So here we can write it as alpha is equal to lambda m by lambda infinity. This relation is known as Ostwald's relation for conductometric titrations. Now, if we plot lambda mc against 1 by lambda, we get a linear plot which gives us the value of Ka, that is the dissociation constant of the acid. Therefore, the Ka, it can be determined only when lambda to the power alpha is known. So here in table 6.1, molar conductivity values of nitric acid in methanol has been listed. So which has been found from this graph. From this graph, this plot shows lambda m by c versus 1 by lambda m, which is a straight line. Now the slope for this graph gives is equal to Ka into lambda into alpha to the power 2, which gives Ka value to be this. But in the case of weak electrolytes, it is not possible to obtain the limiting molar conductivity value. So thus, by extrapolation of molar conductive value to zero concentration is mostly followed as it is done with a for a strong electrolyte. So, for the particularly for weak electrolytes, we use the Coleridge law of independent migration, and this by which is given in this equation. So all the terms on the right hand sides are for strong electrolytes, and thus we can calculate the value of the weak electrolyte, that is acetic acid, from the known values. So the values of lambda m for sodium ethanoate or that is sodium acetate and hydroxy acid, are known. We substitute these values in the above equation and we find out the value of lambda alpha for CH3COH. So if the molar conductivity is this, the degree of dissociation has been calculated is equal to lambda m by lambda to the power infinity, which is 0.125. So first, this is how we apply conductometric titrations for the determination of Ka. So then comes ionic product of water. Now we know the ionic product of water, that is Kw, is given as H concentration of H plus and into concentration of OH minus, which is Kw. Now if the concentration of ionized water is C, then C of H plus is C of OH minus is equal to C. Totally it is given as C. So therefore the molar conductivity of hydrogen and hydroxyl ions at the very small concentrations existing may be taken as equal to the accepted value. So therefore equation 4.8 can be used, and lambda m is equal to kappa, or C is equal to kappa by lambda m. This is equal to K by lambda of H plus lambda of OH minus, and by putting all the values we find out the conductivity of pure water. We know it is 5.8 into 10 to the power minus 6. Then we can calculate the concentration of C by substituting the values in equation here, and ultimately we find Kw is equal to 1.12 into 10 to the power minus 14. Since the activity of the ions in pure water, it cannot differ appreciably, the result is very close to Kw, that is the ionic product at 398 degree Kelvin. 398 Kelvin. The result here in the observed conductivity values and ionic products here in different temperatures from 0 to 50 degrees centigrade has been depicted here. So which are almost made from the conductivity measurements. Conductance measurements has also been used to determine the ionic products of other solvents such as ethanol, methanol, and other acetic acids. Now, solubility and solubility product of a sparingly soluble salt. The conductivity of a saturated solution of a sparingly salt, it can be determined by subtracting the measured conductivity from the salt of the pure solvent, that is kappa of salt is equal to kappa of solution minus kappa of solvent. So we also know that lambda of salt is equal to kappa of salt by C, where C represents the concentration. Therefore we can write lambda of salt is equal to lambda of salt to the power infinity, which is equal to lambda plus lambda minus. So therefore the C, or the concentration, can be given as kappa of the salt by lambda plus lambda minus. The limiting ionic conductivities, that is the value of lambda plus to the power infinity plus lambda minus to the power infinity, can be obtained from literature. The solubility C of the sparingly salt can be determined from other processes. Now let us consider a salt, that is AgCl. The limited molar conductivities of Ag plus and Cl minus, they are known from literature. The conductivity of AgCl at 298 K has been measured to be this. Now to calculate the solubility product, we first calculate the concentration of Ag and Cl minus using the above equation, that is C is equal to kappa of AgCl by lambda of AgCl, Ag plus lambda of Cl minus, and we find out the C value is found out to be this. The solubility product for AgCl can be expressed as K is equal to C into Ag plus into C of Cl minus, that is concentration, that is C square. So the substituting the values in the above equation, the solubility product for AgCl is equal to C square, that is 1.65 into 10 to the power minus 2 whole square, which gives rise to this. So that is why this is how solubility product can be measured from the conductance values. Then comes conductometric titrations. The principle of conductometric titration, it is based that during the titration, one of the ions is replaced, and invariably these two ions, they differ in their ionic conductivity. So as a result, a endpoint is achieved. Now, in order to reduce the influence of errors in the conductometric titrations, the angle between the two branches, it should be as small as possible. So therefore, the following rules have been found to be useful during conductometric titrations. The smaller the conductivity of the ion which replaces the reacting ion, the more accurate is the result. The larger the conductivity of the ion of the reagent which reacts of the cation, the more accurate is the angle of titration. The titration of a slightly ionized salt, it does not give good results. So since the conductivity it increases continuously from the starting, hence the salt present in the cell, it should be completely dissociated, and it should also be a strong electrolyte for better results. Throughout the titration, the volume of the solution is always increasing unless the conductance is corrected, non-linear titration result. That is why it is important the correction that the conductivity is a linear function of dilution. It is only true for the first approximation. In the interest of keeping V small, that is the volume small, the reagent for conductometric titration is ordinarily several times more concentrated than the solution is being titrated. A microburette is particularly used for this purpose. The main advantages to conductometric titrations are it's applicable to very dilute and colored solutions that involve relatively incomplete reactions. For example, which neither a potentiometric nor can serve is the neutralization titration of phenol. In conductometric, neutralization titration of phenol has been successfully applied. Acid-base titration, particularly, they especially occur at trace levels. So this has been also been successfully achieved by conductometric titrations. Some typical conductometric titration curves have been represented here. Now, here in figure 6.2, it shows the conductometric titration curve of a strong acid versus a strong base. Now, before the addition of NaOH, the conductance is high because of the presence of the mobile H plus ions. Now, when the base is added, the conductance fall deeply. It forms steeply due to the replacement of the H plus ions and the reaction of the OH minus ions to form the undissociated water. This decrease in conductance, it continues till the equivalence point is achieved. At the equivalence point, the solution contains only NaCl. So after the equivalence point, the conductance rises sharply due to the large conductivity of the OH minus ions. So this is how a conductometric curve is represented for a strong HCl versus NaOH. Now, let us consider the conductometric titration curve for a weak acid, which is a strong base, that is acetic acid versus NaOH. So, initially in this curve, the conductance is low because of the very weak ionization of the acetic acid. Now, when the base is added, there is decrease in constant conductance, not only because of the replacement of H plus by Na plus, but the dissociation of acetic acid is further suppressed due to the common ion, that is the acetate. But as soon the conductance it increases So figure 6.4, it shows the conductometric titration of strong acid, that is H2SO4, versus weak base, that is dilute ammonia or ammonium hydroxide. Now figure 6.5, it depicts the conductometric titration curve of a weak acid, that is acetic acid, versus a weak base, that is ammonium
Excuse me,
hydroxide.
ma'am.
Ah, yes.
Figure 2 and 3 are not audible. So
Figure
repeat
2,
again.
figure
2
2
and
and 3.
3. Yes.
Uh, um, this 6.2 and 6.3.
Yes, sir.
Okay, okay, okay. In figure 6.2, the conductometric titration curve of a strong acid, that is HCl, versus a strong base, that is NaOH, is shown. So now when you look into the curve, before NaOH is added into the solution, the conductance of HCl is very high because of the presence of free H plus ions. Now when the base is added, the conductance it falls because the H plus reacts with the OH minus of the sodium hydroxide to form undissociated water. Then this decrease, it continues till an equivalence point is reached here. Then at the equivalence point, the solution now it contains only NaCl. So then the equivalence point it increases because of the presence of OH minus ions, free OH minus ions that are highly conducting in nature. So here figure 6.2, it shows a typical conductometric titration curve for HCl versus NaOH. Now, in the second case, we talk about the conductometric titration of a weak acid with a strong base. A weak acid, that is acetic acid versus NaOH. So initially, the conductance remains low because acetic acid is a very weak electrolyte and it is ionizes very low. So after the addition of NaOH, the H plus ion is not only replaced by Na plus ion, furthermore, the dissociation of acetic acid is suppressed due to the common ion effect of acetate. So, but this, as it is suppressed, the conductance then again increases on adding sodium hydroxide because the sodium hydroxide it reacts with acetic acid present in the solution to form sodium acetate, and we know that sodium acetate is a strong electrolyte. So this increase in conductance it will continue till the equivalence point is reached. Now once at the equivalent point, the total hydrolysis of CH3, that is sodium acetate, is occurred, and beyond this the conductance increases more rapidly because of the presence of OH minus, the free OH minus from NaOH. So figure 6.3 it shows how a conductometric titration curve looks for acetic acid versus sodium hydroxide. Next, we will talk about the conductometric titration of a strong acid with a weak base, that is sulfuric acid versus dilute ammonia or ammonium hydroxide. Initially, because of the presence of sulfuric acid, the conductance is very high, and then it decreases because the free H plus ions are not available. So, but after the endpoint has been reached, the graph becomes horizontal as it is shown here. Since the excess ammonia here present in this solution, they cannot be ionized and they react with the sulfate present in the solution to form ammonium sulfate, and we know ammonium sulfate is a very weak electrolyte. So figure 6.4 it shows a typical conductometric titration curve for strong acid, that is H2SO4 versus ammonium hydroxide. The next case that we will consider is the conductometric titration of a weak acid, that is acetic acid, versus a weak base, that is dilute ammonia or ammonium hydroxide. So the nature of the curve before the equivalence point is similar to that curve obtained by titrating weak acid versus a strong base. This point it is almost similar to that obtained by titration of a weak acid and a strong base. After the equivalence point, this is the equivalence point. After the equivalence point, the conductance it virtually remains same because the weak as base, that is the ammonium hydroxide, it does not conducts and it remains, and it is not, it is a weak electrolyte, that is why the conductance does not change much. So figure 6.5 it shows the conductometric titration curve for acetic acid versus ammonium hydroxide. Now what happens if we take a mixture of a strong acid and a weak acid versus a strong base and a weak base. Here we have a mixture. So this is how in figure this 6.6 typically the mixture will look like. Here we have two breakpoints. So the first breakpoint, it corresponds to the neutralization of the strong acid. So first, then when the strong acid it is completely neutralized, then only the weak acid will start neutralizing. So this is indicated by the second breakpoint, which corresponds to the neutralization of the weak acid, and this followed by the conductance of the increase. Here the conductance increases because the OH minus are present excess in the solution if the base strong base is taken. However, when the titrant is a weak base, it remains constant. Now, as you can see, if NH4 is taken, which is a weak titrant, so the conductance remains as such. However, when we take sodium hydroxide, it increases. This is a typical case when a mixture of a strong acid and a weak acid versus a strong base or a weak base is employed. Now, conductometric titration has also been employed for displacement or replacement titrations, and a typical curve is shown in figure 6.7. So, when the salt of a weak acid is titrated with a strong acid, the anion of the weak acid is replaced by that of the anion of the sorry, is replaced by that of the strong acid, and the weak acid is itself present in the undissociated form. So similarly, when you add to the strong base of to a weak base, the cation remains, the weak base remains, the cation it disintegrates, and the weak base remains as such in its undissociated form. So for example, if HCl is added to zero point 0.1 molar of sodium acetate, then the curve shown in 6.7, here it is shown, this type of curve is formed. So the initial increase in the conductivity is because of the chloride ion, is that the chloride ion is slightly greater than that of the acetate ion. Now when the replacement is totally complete, the solution it undergoes sodium, it has sodium acetate that will suppress the ionization of the free acetic acid. So we see a negligible increase in conductivity. But after the equivalent point or the end point, acetic acid is sufficiently ionized that affects the conductivity, and we see a rounded portion of the curve. Beyond the equivalence point, when HCl is present, the conductivity it increases sharply. So that is why here we see a graph like this. Then conductometric titrations have also been used in precipitation and complex formation titration. A reaction that is made on the basis of conductometric precipitation titration is provided by the reaction product, or is it is a actually it is a stable complex in nature. The solubility of the precipitate should be less than 5%. The addition of ethanol is sometimes recommended so as to reduce the solubility of the precipitations. Here a typical curve is given in figure 6.8, which shows the precipitation titration of ammonium sulfate versus barium acetate. If the solubility of the precipitate was negligibly small, the conductance at the equivalence point should be given by AB, by this here, which is AB and not AC. So the addition of excess of reagent, it depresses the solubility of the precipitate, and if the solubility is not too large, then the position of point B can be determined by continuing the straight portion of the arms until they intersect. So this we have to intersect these points to find the actual endpoint. A slow rate of precipitation, particularly with microcrystalline, they prolong the time of titration. So here the addition of ethanol plays an important role. If the precipitate has adsorptive properties, then occlusion may also occur, and the result may also be full with errors. So in spite of certain limitations with the precipitation method, a large number of precipitation titrations have been carried out. The silver nitrate, lead nitrate, and lithium sulfate, lithium oxalate has also been used in precipitation reactions. However, addition of ethanol has been mandatory in all these reactions to reduce the solubility of the precipitate. Now, the conductometric titration method is not very well suited for the study of redox reactions, because almost all such reactions must be carried out in presence of large excess of acid or base, which actually makes the measurement of conductance difficult due to the redox nature of the reaction. So a typical example involves Fe2 plus with potassium permanganate. So although the reaction proceeds like Fe2 plus giving rise to Fe3 plus and MnO4 minus getting converted to Mn2 plus, the fraction of hydrogen ions thus removed is very relatively small. The entire change cannot be measured with accuracy, and thus redox titrations are not usually been applied for conductometric titration by measured by conductometric titrations. So next, coming to application of electrogravimetry. Now, as we know, electrogravimetry measures the weight of the material before and after the electrolysis process, and particularly it measures the weight of the electrodeposit. So first, there are two types of electrogravimetric methods that we came across. One is constant current electrolysis, that is electrogravimetry without potential control, where the electrodeposition is carried by keeping the constant current and the applied potential is increased. So, and the other is constant potential electrolysis, where the electrodeposition, it is also called as potentiostatic method, where the electrodeposition proceeds. The potential of the working electrode is maintained at a constant level with respect to the standard electrode, that is SCE. So though these techniques are very simple and sensitive in their nature, the it is limited by very it has the determination of deposition of small mass becomes a very difficult task. Another limitation with this method is that it requires both washing of the electrode before and after the process, so as to remove the formation of the insoluble substances that get adhered to it during the whole process. Thus, electrogravimetric methods, they are limited to detection of metals which can give smooth and good deposits. The physical characteristics of the deposits, they depend on the nature of the material that is used. So both current and constant potential gravimetrics, they have wider application in quantitative identification. So a summary has been provided here. It is used in quantitative analysis. Like this technique, it involves the deposition of the metallic element upon a cathode. It followed by subsequent, after the electrolysis, the process after the electrodeposition, the cathode is again weighed. This technique has also been used to be used in determination of metal from their mixture separation. For example, electrogravimetric methods have been used for analysis of copper based alloys. So before and after, the weight of the alloys have been measured, and with this we can actually go for quantitative analysis of different elements. So like under any other gravimetric method, electrogravimetry also works when accurately weighable amounts of the analyte are present in the sample. This technique is not very much useful for analysis of trace elements. However, it is still useful for the analysis of a particular alloy. So here in table 6.2 and 6.3, some of the examples of applications have been used. In table 6.3, the applications of electrogravimetry has been listed, where constant current has been used. Like as you can see, the analyte is Ag plus, it deposits as Ag, and platinum cathode electrodes have been employed, and the conditions are maintained as alkaline cyanide solution. For constant potential electrolysis, here other elements that can Ag is taken as analyte. The potential versus Sc has been kept constant at plus 0.10. The electrolyte taken is acetic acid and acetate buffer, and copper and other heavy metals that could be present has been indicated. So this is one use of quantitative analysis of electrogravimetry. Then second use lies in separation. It has been used for separation of one species from another in solution by selectively plating it out, that is through the process of electroplating, and removing it totally from the solution. This method is used to remove interferences, particularly in electrochemical methods. They are also used in simultaneous depositions. A mixture of copper and lead can be determined by the deposition of copper in the presence of nitrate ions at the cathode. So, where lead is deposited as PbO2 at the anode, this is also electrogravimetry is also used in preparative organic chemistry, like where organic compound undergoes a series of redox reactions at particular known potential. Then it is possible that we can know about the starting material, and by subjecting it to different electrolytic reduction reactions, we can the side reactions can be minimized, and other it is also economical and highly beneficial, and the purity is also known. So now coming to applications of colorimetry. Sorry. Applications of colorimetry. So the basic relationship that we have found out, we have studied earlier, is out of the mass deposited can be found out given in this equation. Basically, colorimetry is of two types, that is colorimetry which occurs with a controlled potential, and the second which colorimetric analysis which can be performed with constant current. So in the first case, that is the colorimetry with controlled potential, the substance must react with 100% current efficiency. The completion of the reaction is indicated when the current decreases, practically it comes down to zero, and the amount of the substance that is either produced or consumed at the electrode is determined from the reading of the coulometer in series with the help of a device. In the second method, that is when coulometry is performed at constant current, a solution of the substance is to be determined. It is electrolyzed with a constant current, and when the reaction is completed, the quantity of electricity passed, Q, is given as I into T. The time can be measured accurately with a stop flow, and using from the value of Q, the mass deposited at the electrode can be known. So, application of coulometry, the coulometric method has been considerably, it has actually more scope and precision than electrogravimetry. Here in coulometry, a control potential, that is normally a mercury cathode, is preferred, since the optimum control potential for a given separation is determined from polarigraphic data with the dropping mercury electrode. In general, here table 6.5 has shown the deposition of metals at control potential of the mercury electrode. Some of the applications have been listed here. By means of controlled cathode potential technique, it is possible to determine simultaneously some metals that are present in a solution. This has also been used in the determination of many metal ions. Like for almost 55 elements have been determined by cathodic reduction of metals. More than 2 dozen metals have been they form amalgams with mercury, and they have been understood by this controlled potential coulometric methods. Now, the general procedure for performing coulometric determinations at controlled potential of the mercury electrode, this is a general procedure. The electrolyte, mostly 50 ml, is taken in a cell, and a stream of nitrogen is passed through it to remove any traces of impurity and particularly oxygen. So the mercury cathode, it is involved through the stopcock. Then after following the experimental process, a known volume of the sample is taken in the cell, and electricity and the electric current is passed through it. The electrolysis occurs, and from the value of M, and from using the measuring the value of Q, we can find out the volume of M that is deposited. So here in example, it has shown the separation of nickel and cobalt by controlled potential coulometer. So the reagents that are used has been standard nickel and cobalt ion solutions, which have been prepared by dissolving respective ions in water. So pyridine has been used. The electrolytes have been 1 molar pyridine and zero point 0.5 molar chloride ion, and the pH was adjusted. Platinum electrode has been used. So the procedure was followed, and after the passage of electricity, the total quantity of electricity that has been passed during the reaction was studied from the coulometer, and the mass of the each metal deposited at each potential was found out using this relationship. Then is multi-step control potential electrolysis. The determination of simultaneous several ions in the same solution is possible by this method. Suppose a sample solution containing several ions such as Cu2 plus, bismuth 3 plus, lead and zinc, they have been determined by this technique. When the cathode potential is varied at different volts, the potential, and then by controlling this potential, the sample can be analyzed, because at respective potential a respective metal can be known. The controlled potential coulometry has also been used in microanalysis. It is popular than electrogravimetry because it avoids the final step of weighing the product. So the various steps of drying and weighings can be avoided. This technique is very accurate, and for the determination of even zero point zero 0.01 to 1 mg with an accuracy of plus minus 0.5%. This has also been used for analysis of radioactive materials. The coulometric materials have been widely used in the determination of uranium and plutonium. So, by monitored by that are widely used in radioactive analysis or in nuclear chemistry. This was also used for continuous monitoring of gas streams. Determination of trace level of oxygen has been done by controlled potential analysis. So here a porous silver cathode and a cadmium anode is used. The respective cell reactions have been at cathode and anode has been depicted here. The porous silver cathode, it breaks up the incoming gas into small bubbles, whereas the reduction of oxygen takes place within the pores. The hydroxyl ions that are formed during the reduction process, they react with the cadmium anode and they form CdOH whole 2. So as a special feature of this cell is that there is no external power is needed. So there is no need of potentiostat. The current pass through the standard resistor and the potential drop is recorded. The oxygen concentration is directly proportional to the potential that is applied. The setup has been used for determination of oxygen, and it can also detect oxygen purity concentration from 1 ppm to 1 percentage. So controlled potential colorimetry has also been used for electrolytic determination of organic compounds like TCA or trichloroacetic acid. They are quantitatively reduced at a mercury cathode colorimetric method. It permits the analysis of these compounds with almost an accuracy of 0.1%. So this also possible for the synthesis of new compounds using colorimetry, since the chances of contamination and the use of chemical reagents are totally avoided in this case. So it is also used for determination of n values, where n determines the number of electrons involved here. The control here in picric acid, it is reduced in a mercury cathode, where the n value of the reaction has been found to be 18, which involves the number of the electrons required for this reaction. So controlled potential coulometry has also been used for this purpose. Then comes the application of coulometric titration. Coulometry as control potential, it has limited application, but when controlled coulometric titration, they have been developed for all types of volumetric titrations. So some of the important applications that they have been used for us, like neutralization reactions, so that this involves the titration of a strong acid with a strong base. So one of the main advantages of coulometric titration of acids is that difficulties associated with the presence of carbon dioxide that is present in the solution is easily avoided. The carbon dioxide is just removed by passing the vacuum or nitrogen gas, which removes the traces of carbon dioxide from the system. So the presence of any substance that is reduced more easily than hydrogen ion or water, or which is oxidized more easily than water, will interfere. So when this interference can be is one of the interference the avoidance of these interference is one of the main advantages of coulometric titration. So here the titration of a strong acid and weak base in the hydrogen ions is generated at a platinum, and the given is this. So the precipitation and complex formation reaction, a large number of coulometric titrations have been developed in literature. The generating electrode consists of a heavy silver wire, and it has been shown in unit 5 of this study. So the endpoint is detected by mostly by the adsorption indicators, that is by color, by spectrophotometer, or by potentiometry, and this method is very useful for detection of bromide and iodide solutions. Chloride, bromide, and iodide have been generated, have been known from such type of colorimetric titrations. They have been quantified from this, and that also gives good result. So the standard for, but particularly for chloride, the standard potentials has been listed here. The oxidation, they require a smaller potential. The complexometric titration that particularly use ethylene diamine tetraacetate ions, they have been very good for colorimetric titrations because they can form chelates. So the reduction of the ammonium mercury chelate, EDTA chelate, at the mercury cathode gives good results, and they are the complexes that are formed by this method are stable and they give good value. So oxidation, the colorimetric titrations of redox titration, they are of much importance because of in situ generation that we have already read. The conventional volumetric analysis, they are not at all, they cannot handle such reagents. So the in situ generation, that has been particularly useful for determination of bromine ions. So here, table 6.7, it provides applications involving neutralization, precipitation, and complex formation reactions. And here, table 6.8, it shows the applications of colorimetric titration in redox reactions. So, and particularly this, the where for the generation of bromine has been most widely used, is one of the most widely used application of redox colorimetric titration. Then coming to advantages of colorimetric titrations, preparations, standardization and storage, these are actually not necessary. So here this is useful for the preparation of unstable reagent, with like particularly for unstable reagents such as bromine, chlorine, titanium, because they can be generated in situ and they are not, and the conventional methods cannot handle these reagents. They are easy to handle because they require very minute quantities, and micro quantities can be known. The single constant current source can be used to generate the precipitating complexing reagents. Coulometric titrations, they can be readily adapted to automatic titrations as the current control is just done. A number of automatic colorimetric titrators are commercially available in the market that has particularly been used to monitor the environmental pollution. In chloride titrator, 1 Ag plus ion is generated coulometrically. In sulfur dioxide monitors, anodically generated bromine, it oxidizes the analyte to sulfate ions. In carbon dioxide monitors, in which the gas stream absorbed in monoethanolamine is titrated with coulometrically generated base. So particularly in Carl-Fisher reagent, Potter titrators, the Carl-Fisher reagent that is used is generated electrolytically to determine the trace level of moisture even present here. So these are some of the real life applications of colorimetry. So in this chapter, we have come across the various applications of conductometry, electrogravimetry, and coulometry. So with this, we complete this part. If there are any questions, please ask. Okay, if there are no questions, thank you for today.
Thank you, ma'am.